I provided some more examples here. They are simple examples, and I try to explain them today. Please spend some time later on these and try to think more about them, about the orientation and so on for each element that we draw the stress element, and make sure that you understand it, all right? All right, so let's get started with this very, very simple example. We have a bar or a beam, and it fixed in one end, and the question asks us to find a stress at point A, B, and C. And when we say a point, it's in fact a point, but when we draw the stress element, we sort of magnify that point, and we think it is as a square, basically, right? So for this element A, B, and C. So before I draw the stress for A, B, and C, I should think a little bit how these things are going to deform, right? So if I apply a compression, a compressive load like this F here, we know this square at point A and B, and by the way, point C is mirror of point A. They are all going to get compressed, right? They become shorter. So immediately we realize that these elements, they are under compression. So let's magnify this element, and I show them like here, and we draw the stress element for them, all right? So this is point A, right? The point that we want to draw the stresses, and it's very, very simple. This one, we know it has to be under compression like that, the stress like that, right? And we know how to calculate this one. Sigma is going to be F divided by A. And we know A is the area of this beam or bar or whatever it is, all right? So that's very simple. The same is going to happen for this element at point B. It is under compression. In fact, any point at this support is under compression. And the same for point C. All right, so this is basically the stress element for these 3 points. Now, if I want to like be exact and draw them like in a 2D, nice 2D element for later analysis, all I need to do is first figuring out an axis. So it's up to us. We can decide for any axis that we want. Let's say that I go with X, Y, and Z like this one. Let's call this one maybe X, this one Y, and this one Z axis. But it's totally up to us, and there is no rule how we should choose the orientation. But don't forget the right-hand rule, which I explained earlier in previous lectures. All right, so the same axis then goes here. At the corner of this element, then I'm going to have the same orientation. So we keep the original orientation, but it's okay to move them around. So this is then X, Y, and Z. So if I want to draw the 2D element, then my element is going to be a 2D element like this, and my axis is going to be, so I'm looking from the top view, right? If I'm looking from the top view, then this is going to be X, and this is going to be Z. So this is X, Z. Remember, this is letter A. We are looking at point A, and this point A is over here, and we're looking from top. So this is our 2D element here, and this 2D element, it has one stress like that, and following this orientation that we decided, it's going to be sigma X then, right? And sigma X is minus F divided by A, because it's under compression, right? And in this element, we don't have sigma Y and, sorry, sigma Z, because our axis is Z, right? So this is sigma Z. In Z direction, we don't have anything. And also tau xz is equal to 0. All right? So let's do the same things for point B, like this point. So point B, if I put my coordinate there at the corner of these elements, so it's going to be then like that. And I said it's okay to move around those axes, but we are not allowed to change the orientation, X, Y, Z, after we decided for the original orientation, like the one that I draw at the top. So this is X, Y, and Z. And now I can draw my 2D element. I don't care about the Z direction because Z direction, everything for that is 0. So then my element, I draw it over here, is gonna look like this. Stress over there and nothing else, right? And my axis is gonna be X and Y, like this. So this is X and this is Y. And the stress is gonna be the same stress that we calculated, F over A. So in this, for this element then, I just write down that sigma X is minus F over A, sigma Y is 0, and tau XY also is 0. So you got the idea, right? So the same scenario for point C, which is, we cannot show it like on the beam here, but it's the mirror of point A basically. We put our axis at the corner of these things. So this is X, Y, Z, X, Y, and Z, right? And now if I look at these elements, either underneath, let's say I went underneath of this one and I'm looking at this element, then probably this is what I'm gonna see. I'm gonna see, let me find, okay. So what I'm gonna see then is gonna be X here. Imagine that I'm underneath and I'm looking at this one, right? So I'm gonna see X and Z. So this guy is X, this one is Z, and this is point C, right? This is point C. Okay, and on this one, again, the only things that we have is sigma X. The rest are 0. Sigma X minus F over A and sigma Z 0, tau XZ is equal to 0. Right? So this is the state, the stress state for element A, B, and C, basically. Right? Very, very simple and straightforward. I believe it's easy to follow. Now let's spice things a little bit up. And the same beam, this time, it is under bending, basically. We apply load P over there, right? And this load P try to bend everything. So if we try to exaggerate this load P, try to bend these things, something like that, like it's gonna bend like that. So we know that if it bends like that, then the top portion of this beam is gonna be under tension, and the bottom is gonna be under compression, right? And we learned before in module, I believe 5 or 6, the bending, when we discussed the bending, we said when we move from top when it is under tension to bottom when it is under compression, somewhere in the middle there is nothing, right? Which we call it a neutral axis, or in a plane scenario, it is called a neutral, basically plane. Like if we show it in a, let's say a 3D scenario, like this plane in the middle, if I could draw it for you guys. So like this plane, which passed through this basically center, right? This view. So this is what we call it a neutral plane. Neutral plane, right? And then you learn that if at any cross section, if you look at the cross section of this beam, let's say if this is the cross section, at any point, then this axis which passed through the centroid, we call it neutral axis, right? So this is centroid, this is our cross section, and this is what we call it the neutral axis, basically. So this is what we discuss in bending, the topic in bending related to bending, right? So simply from now, we can, from what I draw, we can figure out that because of this load P, this element at A is under tension, right? We can guess because it is at the top, so it's gonna stretch them. What about point C? Point C is under compression. This square, this element is gonna compress basically. What about point B? Point B happened to be in the neutral axis, so it's gonna be then 0, right? So remember, this is our point, basically A on the cross section. This is our point B on the cross section. And this is our point C. Oh, let me call this one the centroid, maybe point O, so we don't get confused with point C. All right, so O is this, the centroid, which passed through the neutral axis. Now our goal is to draw the stress element for A, B, and C. Let's do that. So from what I just explained, now it should be easy for us to figure out this element is under tension, right? This is point A. Point B, nothing is going on there, and point C is under compression. All right? So if we choose the same axis that we picked before, X, Y, and Z, so this is X, Y, and Z, right? So what we are gonna have, let's say for point A, for point A, I'm gonna have here a sigma, which is my divided by I. Remember, the thing was under bending, right? And I have to put the point for Y for point A, basically. Let me draw the cross section again here. This is the cross section. Let's say this one is B and this one is H. So this is B, this is H, and so this is our neutral axis, all right? We have our neutral axis, and which we call it point O. This was point A, neutral axis, and we know how to calculate I for this one. I about neutral axis is gonna be 1/12 BH3, all right? So what is then Y A? It's gonna be H/2, and it is under tension. So for point, so this is point A. For point B, everything is 0. Nothing is going on there. Sigma X is 0, sigma B is 0, sigma Y is 0, and tau X, Y is 0. Nothing, we don't have anything there. Here, we just have sigma X. And then when we go to point C, this one at the bottom, point C now, we can say simply that it has a sigma X, and this sigma X is minus my divided by I, which this Y is again is H divided by 2, all right? So point A is under tension, point C is under compression, and point B, nothing is there, right? So if then somebody, let's move back, ask us to design this beam, probably we should design it for point A or for point C, all right? Not point B, because point B, it doesn't have any stress. So is there any questions so far, guys? Are we good? All right. So now let's combine these two together. What we just learned for when this beam is under compression and also at the same time when it is under bending, all right? So we just treat them differently. We treat this example similar to example 1 and 2 separately, and then we combine them together. So that's simple. So what then I do is I say for point A, I'm gonna have a tension. I'm gonna have a tension which comes from the bending. And we know the formula for that one. So this is point A and we are point A. So I'm gonna have a tension which is MYA divided by I, which we just calculated. And also I'm gonna have compression which comes from the other things that we just saw. So this is sigma x also, this one is sigma x, and this one is minus F divided by A. So if I want to draw my element here, then my element, the stresses are going to be only one thing here. And that thing is going to be sigma x m YA divided by I minus F over A. All right, so this is the stress element for point A. Still sigma Y is 0, or whatever we call it, sigma Z, I guess. The other two, they are 0, all right? What about point B? So point B, the only things that we have is the compression. And that compression is going to be minus F over A. What about point C? So this is where it gets interesting. So point C is from bending, example 2, we learn it is under compression. So this is C, and sigma x is minus F divided by A. Sorry, from the bending we learn it is under compression, and the compression is minus MYI, right? Let's move back one step to example 2. See, this is point C. Point C we learn because of this bending load, it is going to be negative because it is underneath and that's under compression, all right? And also we are going to have a compression because of that axial load. Another sigma x minus F over A. So if I draw the stress element for this guy, it's going to be then, it's going to be stress like that, which again, it is in x direction, and it is my divided by I minus F over A. So this is YC, right? So we see between point A and B, A and C, A, B, and C, the worst case is point C. Why? Because we see point C, these two numbers, they are adding up. They are negative, but they are helping each other, compressing point C more. While this point A, the compression load, try to compress it, but the bending sort of release the stress a little bit. So if these things is going to break, it's going to probably break at point C, at least in theory, all right? So that's why when we want to design a beam like this one, it is important to find out which point to draw the stress element and base our calculation. Not point A, not point B, it's going to be point C. Why? Because point C is going to be compressed because of this load, axial load F, and also it's going to be compressed because of this bending load, all right? So I believe it is simple, but please, if still if you cannot follow, later spend more time on this one. This is super, super simple, but I've seen many students, even in fourth year and even in grad school, they have trouble understanding this simple concept. And later when they want to calculate the stress for their capstone project or maybe other things, they cannot really find out what is the critical point and how to calculate the stress element, all right? So now let's change things a little bit now with example 4. Now we have the same beam, but this time we are applying the load horizontally, right? Unlike the previous example, example 2, which was a vertical load. So let's draw the stress element for this one now, all right? So the first step is, again, to find out how this beam is gonna bend. So it's easy to find out, and we can exaggerate. If I apply this load, we easily know that it's gonna bend like that, right? Please accept my drawing. It's gonna be bent like that. And if it's bending like that, so immediately we know that this side of the beam is gonna be under tension, and the other side is gonna be under compression. All right? So where is the neutral axis on this beam? So the neutral axis is gonna be a plane when we move from tension to compression, right? It's gonna be then, let me get rid of this messy drawing first. So now that we figure out where is tension and where is compression, the neutral plane is gonna be this one, right? All right, so this is the neutral plane, right? Parallel to this plane that point B is there. Let's write it down there. Neutral, not that one. Neutral plane. All right. Now we know that if this beam starts bending, it's going to bend for that section that we are discussing, like here, is passing through point A and C. So probably you guess now that point A and C, the stress is going to be 0 for them, right? Because they are passing through the neutral axis. So let me draw the cross section one more time here. So this is our cross section. And this is B, this is H. Remember, this was B, and this distance here was H. Okay, this is our cross section. But be very careful, because now our neutral axis is this guy. All right, so this is the neutral axis. Okay, and where is point A, B, and C? So this is point A, this is point B, and this is point C. Okay, I'm just drawing the cross section for those points that we are interested in finding stresses. Okay, and as you can see, right, because of this load that we just applied there, and the way that this beam is bending, stress at point A and C is going to be 0 because they happen to be on neutral axis. So sigma is 0 and sigma is 0. All right. What about B? Well, stress at point B is under bending. Sigma is m, the distance to neutral axis, which is B divided by 2. I about neutral axis, okay? And here you have to be careful because I about neutral axis is gonna be 1/12. Remember I told you to draw two brackets, and the one that the neutral axis is crossing it has the power 3, so it's gonna be HB3, all right? Unlike the previous one, which was, we write it somewhere here, yeah, it was 1/12 BH3 because neutral axis crossing this H, okay? This one, the bending happens like that. We find the neutral axis, which pass through point A and C. So stress at point B is going to be like that. So if I want to draw then the stresses for each element here, I'm not going to have anything, sigma x, sigma, or let's just write down all of the stresses are going to be 0, all right? Stresses for this one is going to be 0, nothing on these two elements. This is A and this is C. And point B, this guy is going to be under tension with the stress that we just calculate, sigma is going to be equal to M B divided by 2 and I about neutral axis, right? Which we said if this is B and this is H, this one is 1/12 HB3. Okay, so this is the stress element for point B. And if somebody asks you to draw the stress element for point D, which is point D, which is the stress element like mirror of point B, let's say somewhere around there, point D, okay? So point D, the stress is going to be, you can guess, it's going to be very similar to point B, except it's going to be under compression. Right? So sigma is going to be minus M B divided by 2 divided by I about neutral axis. Okay? So this is point D then. Oh, hard to see. So point D. Hope it is clear now. But if it's not, please ask now if you cannot follow any part in these 4 examples. Do you guys understand what's happening now?
I don't really follow that the length B is divided by 2. I'm just trying to visualize. Yeah. If you can please go back to the previous slide.
Okay, so look at this. Look at Mohammed. Look at this cross section.
Yeah.
So this is the cross section, right, of the beam, and how the bending happens. Bending happens about this vertical axis. Do you agree?
Yeah.
Look at this plane. When you apply this load F, this plane is going to be your neutral axis, right? So when you look at the cross section and on this image, everything is going to bend around this line. Let's call this line maybe something like E, all right? So this line, this long line, everything is going to bend around that line, okay? So if things are bending around that line, then it means it is our neutral axis, all right? So, and if it is our neutral axis, then remember the formula that we learned for bending? Sigma was my divided by I. We said always I is the moment of inertia about neutral axis, and y is the distance between the point that we want to calculate the stress to neutral axis, right? It's just in this example, we flip everything's 90 degree. Rotate everything's 90 degree, or you just rotate your notebook 90 degree, or a screen now 90 degrees. It's going to be the same problem that we learned before, except it is, instead of being, except our neutral axis being horizontal, it is now vertical, right? That's the same exact problem. It's just we have to maybe turn our head like that one, and then it's going to be the same problem. Okay? Is it clear now?
It's clear. Thank you.
Good. So now let's solve an example a little bit more complicated. Okay? Let's say we have maybe a bracket in form of a C shape or whatever, like this one. Okay, for some reason we build this one, and then we apply this to load F, right? So like always, this is the way that I suggest start solving a problem. Try always visualize things by like exaggerating, try to see how these things are going to deform and how it's going to break. For example, let's say these things, you built it and now you are applying like this load at the two sides. So what you're trying to do, you're trying to open up this C basically shape bracket, right? You're trying hard to open up these things. So if you're trying to open up these things, then probably you can guess if these things is going to break or crack, where it's going to be. Any guess? It's going to be point A, or it's going to be point B, or it's going to be point C. Where do you think it's going to start cracking?
B.
B. Okay, Thomas is saying B. Other people, you agree?
Yeah, B.
B. All right. Makes sense, right? Because if you apply the load like that one, you're trying to open up everything, and then you can think of like this section, the vertical section, more like bending. Again, I try to exaggerate. It's bending like that, right? Let's try to open up and bend like that. So if you try to open it up and bend like that one, then probably you can guess, because of this load, this section is under tension or compression? Tension, right? You can think of this beam, that the curved beam that I draw. This side is going to be under tension, and this side is going to be under compression. So that's the first step. If you understand this one correctly, then the rest is just simple math. We can figure them out, and it's easy, right? So, and Emily and Thomas, they were right. If these things is going to break, it's going to be point B, all right? But let's see how math is going to solve this problem for us, okay? So far, it's just some simple visualization and exaggeration. So like always, we start with the free body diagram, and we draw the forces with having this in mind that everything has to be balanced, right? So we are interested in the section that passed through point A and B, like this section. So we section this beam like that. So the external load, so we have an external load which we call it F there, right? So because we are in a static, somewhere this load has to be canceled, right? So we know that there is no choice to have a load F there, right? To balance it. Otherwise, things start moving down, but we are in a static and things has to stay there, right? So we have to have an internal load. So this is an internal load, internal, right? Internal reaction. So what else? Let's look at this load F, this external load F. This external load F try to spin things, right? Try to, let's say about this point on the image on the right, this load F try to rotate things, okay? Try to create a moment. This is F. And let's say this distance is like this distance from here to here. Let's say this distance is B or D, whatever, doesn't matter. Let's say D. Okay, this load F try to create a moment about this point O or B or O in the middle of between A and B. And this moment we know it has to be counterclockwise, all right? So we try to rotate everything like that. But again, we are in a static, things has to stay there. Things are not allowed to move. It means something in this cross section has to prevent this spinning, right? So to have that, then we have to have a reaction M here to cancel this M. This M, we know it is F multiplied by D. So this M has to be F multiplied by D, but opposite direction to cancel. Okay. So this is our basically two reaction at this cross section. We have one F there, which you know this F comes from here, and we have a bending M, which is like that. So let's treat them separately and see how it's going to look like. So this first one, this load F, all right, this load F creates a stress on this cross section. Let's draw the stress on that one. We know the stress is a distributed, basically, load, and it's going to be, let's say, everywhere the same. All right. So this is going to be our stress here. And we know how to calculate that one. We know that this sigma is F divided by area. And area, we know what it is, right? So that's simple. What about this bending? Okay, this bending, this requires a little bit of your visualization and imagination maybe. All right, so how it's going to bend? You guys tell me. It's going to bend about which of these axes? The axis that pass through point A and B, or the one perpendicular to that? Or in other words, which of these two axes that I draw is going to be my neutral axis? Try to visualize how things are going to bend, and then look at this point A and B.
I think it's going to be rotating around the one that doesn't go through B and A.
Exactly. So Emily is right. So if you see how this thing is going to bend, look at the image at the top, right? So this M, we try to bend things, try basically to bend this line. Let me draw this line. This line A and B, try to bend it or spin it maybe. It's a better word, like that, right? It's going to be something like that, right? This like point A is going to come down, becomes point A prime, and B is going to go up there, becomes B prime. Okay? So then the bending happens about this axis, N, A, okay? So now you guys tell me, from this bending moment M, point A is going to be under compression. Point B, you see, point B went to B prime. It is stretched. It is going to be under tension then, right? And also something that we confirm here. Here, remember we said B is under tension, A is under compression. The same things here. So if I want to draw the stress element for A and B, so, but before that, let's draw this one here. So point A is going to be then, point A is going to be under tension, compression, and point B is going to be under tension, all right? And then the rest, we know, like these 2 points are the maximum. As we move from point B to neutral axis, things become smaller and smaller until they become 0. So like point B here is small tension until 0, and then we switch to compression. Yeah, it's difficult to show it here, but you got hopefully the idea. tension, and then compression, right? So now let's do the math, all right? Here we know that point A, the stress at point A, is equal to a stress at point B, and it's equal F divided by, let's have some numbers here, and maybe we call this one H, okay, this distance, and this side we call it B. Okay, so in a 3D image, let's say this here is H, and this is B. Okay, so it's going to be then BH, F divided by BH. And here, be careful, we have our neutral axis. So I about neutral axis is going to be 1/12, two brackets, one of them has power 3, another one nothing. So it's going to be BH3. And please, again, later go and check these things and make sure that you understand them. And then we say stress at point A is minus M, right? The distance is going to be H divided by 2, I about neutral axis. Let me draw the cross section, maybe just to make sure that you guys can follow every step, right? So this is our neutral axis. Neutral axis is like that one. So this is the neutral axis. This is H, this is B, right? And this is point B, and this is point A. I just like this cross section. I just imagine this cross section here. I just take it and put it on a 2D view like that. So this is our cross section. So what about sigma B is going to be plus MH divided by 2 divided INA. All right. So that visualization that I told you at the very beginning is going to sort of guide you to make sure that your math is correct. When you know B is under tension and A is under compression because of this exaggeration that you made here, so now you can see B is positive and A is negative. So without too much thinking of which direction is Y, which direction is X, and getting all confused, my recommendation is try to visualize how things are going to be, how things are rotating, which one is your neutral axis, and then the other things just simply follow. Okay. Now that we have all this information, we can simply draw the stress element for A and point B. Let's do it over here. Okay. So we want to draw stress element for A and for point B. So this is point A. And let's say this is our point B. So A, B, all right? So point A, the stress at point A, then is going to be, all right. So stress at point A, let me go back there. Okay. Sorry, let's just start with point A. Point A, we found that we have stresses, two stresses. So then sigma is going to be minus F over BH. See what I'm seeing over here. I'm just writing down what I'm seeing over here. Oh, we made a mistake here, guys, right? Here it was positive. Nobody told me it was positive. See, this F is tension, so this one is positive. F divided by BH. So that's that one. Then we have minus MH divided by 2 I neutral axis. So now you may say that maybe the result is a positive number, and we don't know. It depends on these numbers, right? We don't know. Maybe the result is a positive number, so this stress then is going to be the opposite direction that I draw. Yeah. So it means that we need to have some numbers. We put together the numbers, so we find out if this point A is under tension or compression. What about point B? So point B definitely is going to be tension, and it's going to be F over BH plus MH2 divided by I neutral axis. And as you can see, the stress at point B is bigger than point A, because point A is two numbers. We subtract something from this number, but these two numbers are adding together. And let's see what Emily and Thomas said at the beginning. They said if this thing is going to break, it's going to be point B, right? So meaning stress at point B is bigger, and we see our math confirm that one, that the stress at point B is bigger, okay? So this is how then we treat like problem like that one. Now let's say, let me show you quickly. Okay. A C-clamp, which is like a practical, you guys can see the screen, right? The C-clamp?
Yep.
Yep, good, all right. So C-clamp, probably many of you have seen. C-clamp, we use it to clamp maybe two things together or clamp something to our table. So these things, we can tighten up things, right? So if, for example, I put these things there and I try to tighten up things, now I can tighten it up like that, okay? Now these things cannot move, all right? So when I'm tightening up something with a C-clamp, I'm compressing these two, right? And these two, they apply a reaction. So then it's going to be like that. So this is the two things that I have here. With the C-clamp, we try to compress them. All right? Like that. And the reaction for them is going to be then a load like this one and a load like that. All right? So it is sort of the same problem that we saw now. If this thing is going to break, it's going to break at point B or at point A. We know it's going to break at point B, right? And we know how to calculate the stress for point B and point A. So let's move back to our calculation, which was in fact, what do you have on your note, example 5? Remember we solved example 4, that one, which everybody was confused. Now it is an easy example for you. So example 5, now it should be very easy for you guys to find out. So this is your point B, this is your point A. You know you have to only focus at point B because we know, right? If it's going to break, it's going to be point B. And we know our neutral axis and everything that we need to calculate the stresses for this point. So this will be the neutral axis then. My pen is getting finicky, okay. That's basically the same problem, right? So I about neutral axis is 1/12 BH3, and sigma at point B is going to be force divided by area, which is BH, plus M the distance, and I about neutral axis. I gave this example last year in final exam, and many students again made the mistake of confusing the direction, because usually when we see a cross section, we have a tendency to think of the neutral axis as being this horizontal one, right? But it's not, right? And you saw also in practice, when we, let's say, return back to that C-clamp again, the C-clamp, when you try to tighten something up, so in fact, you're applying a load like that one, and this load want to open up everything. And if this C-clamp is going to break, it's going to be point B, all right?